Yeah, number 18. Here we go. Okay, so this one talks about paired, samples that are dependent, right? So we're basically, comparing to see if one is equal to the other in some cases, or if one's bigger or smaller than the other. We may want to know that in a lot of cases, right? And so our first sample, and it states the hypotheses and stuff for us to kind of break us into this nice and easy, but it says the null and the alternate hypotheses are that mu of the difference, I guess, is less than or equal to 0, and the alternate is that mu of the difference is greater than 0. So it says the following sample information shows the number of defective units produced on the day shift and the afternoon shift for a sample of 4 days last month. At the 0.05 significance level, can we conclude there are more defects produced on the day shift? So that's the greater than, right? That's the alternate hypothesis. Okay, is that the day shift has more. Okay, so what do we do? Well, the formulas are given to us. If you go back to page, there it is, first on page 365, that the formula for a paired t-test is that t is equal to the mean of the difference between the paired or related observations, and S sub d divided by S sub d, which is the standard deviation of the difference between the paired or related, and n is the number of paired observations, and we got to take the square root of that. And it gives you a really good example here, going through some appraisals and how they would do that. I do think that they got a little misprint at the bottom where it says difference d and it says 46. I think that should be 4.6, because then that would make it a little bit easier. 7 minus 46 wouldn't be 2.4 if you go over to the next column, but in any event. Okay, so I've just entered the data like they have it, okay, presented in the deal, and your guys' is similar for 18, so I put it in the data. I got 10, 12, 15, and 19 in the day shift, and 8, 9, 12, and 15 for the afternoon shift. Okay, and so I want to, at the 0.05 significance level, can we conclude now? We got to find our degrees of freedom. So let's first state our decision rule, right? So we've got 4. In this case, we only use the 4 minus 1 because we're basically combining these to compare them. So we're only going to use the 4 minus 1 to find the degrees of freedom. So my degrees of freedom is 3, and it tells me to use the 0.05 significance levels like you guys have in the back of the book. And mine's one tailed, so 0.05 degree of freedom, 3. So I'm at 2.353 for my critical T. Is that the one that's called? Okay, but now I got to do some calculating, right? And so again, if I look back on page 366, it's kind of nice. I can simply say this. I find the difference, right? So 10 minus 8 is equal to, right? I can put that this is equal to this minus this one. Okay, and then I can just drag that along. Okay, and that gives me the difference, and I can add that up. Okay. So I'll just do that as a sum, right, of these. Yep, very good. Okay, but then I got 4 items, and so I want to figure out the mean of that, because ultimately that's what I'm looking for. Should be a little line over that, but that's equal to my 12 divided by my 4, my paired mean, right? So my D that I use in these formulas, this formula and up here, okay, the D is equal to, or the mean of D is equal to 3. Okay, well, now I got to figure out the standard deviation, because I got to know that, right? And the standard deviation is the sum of d minus d squared divided by n minus 1, because it's a sample standard deviation. So this is just our standard deviation formula. Okay, it looks more complicated than that. This part's the variance inside, and then we take the square root of it to find the deal. So it's just our standard deviation formula, which is to take this, okay, number minus our, okay, our mean of d, Alright, so this is equal to this one minus our mean, just like we do in others. I got it kind of the opposite way, and I'll hit my F4, right, so that reference stays consistent. And then I drag that along. Okay, boom. And then I take the square of these, right, so I get rid of the signs. Okay, so it's equal to this to the square to the second power. Okay, I add those up. It gives me, I get the sum of those. But then to find my variance, remember I take the sum and instead of, and that's why I don't do the average when I got a sample. Okay, it would be easy just to do the average of those, okay, which would be 0.5. But when we're doing a sample, we don't, right? We take it times the sample size, or divided by the sample size minus 1. So it's going to be 2 divided by 3, basically, right? Or it's equal to my F7 divided by my sample size, which is 4 minus 1. Yeah, we could have done that math in our head. I know. I like to do that. And then we just got to do the square root of that, right, to get our standard deviation. Okay. And there's, okay, so I've got my labels over here of things that I'm going to need, right, to calculate my t. I'm going to need that d, which is my 3 up here. And I'm going to need the standard deviation of the sample. So I got s is equal to, I know it's way down over here, but that's all right. We'll make that work. Okay, and my n is that one, so we'll make it a fancy color. Okay, I got all the stuff I need then, don't I? I got d is up here, and we'll make that one, I don't know, greenish. There you go. Okay, so I got all my stuff. Right, and so I can just put that in my formula, and that's not a very long formula, so I think I can do that one. It's just simply t is equal to my d, this one up here, okay, divided by, and I'm going to need a parenthesis, probably my standard deviation, which is that one, okay, divided by, I'm going to do another parenthesis, but the square root of my n, I could do that one in my head. The square root of 4 is 2, but I'll go ahead and do this, right, to the, oops, I got to hit my shift key, to the 1 divided by 2. Well, I don't screw this up. I got way too many parentheses. Yeah, I got the right amount of parentheses, I think. Looky there. I came up with that, okay, and my I looked up my critical T was 2.353, and so according to my alternate hypothesis, right, which is that if it's greater than, I'm going to reject it if it's greater than my critical T, which it is, so I reject the null in that case, and then I can assume that there is more defects on the day shift. Okay, I'm going to show you, I think, and I haven't done this, but I think that I can do this using a data analysis one too. T-test paired to sample for means. I think that's what that's called, right? Ooh, T-test paired. Yeah, I think that's what we got is paired. Let's give it a try, see what the heck happens. So my variable range 1 is this one. I'll go ahead and include the label. Okay, and my second one is there. Okay, but I got labels clicked. Okay, my significance or my alpha, it's 0.01 or 0.1, but I want it to be 0.05. Okay, I think that's right. And then my output range down here, I want it to be here. I think I'm okay. Let's see if I get the same answer here. So my calculated T-stat, is that the same? 3.48469. Oh, look at that. I haven't carried it out further. My critical T-stat for a one-tailed is that. Okay. And so I can say that it's definitely greater than, and so I can assume, I can again reject the null, and I can assume that yes, we have more defects. Okay, so how do I want you to do it? Both ways? Sure. Have some fun with it. Enjoy yourself.